Hello, I'm Ivan from the PROSE group at Microsoft. Today, I'll be talking about parsing text files in various standard, ad hoc, and mixed formats. I will present an extensible program synthesis framework that can automatically, without user input, extract tabular data from these diverse formats. The problem we are solving is a common task for business analysts or data scientists. They often need to take a text file and get it into a clean and structured form in order to perform data analysis. These files come in a number of different formats. For example, standard formats like CSV, XML, and JSON documents, and their subtle variants and various configurations. Ad hoc formats like custom logs. Also, these formats are often combined, like for example, JSON within CSV within a log file. Let us look at an example of such a file. This file is in a non-standard format and inspired by a real-world log file. There are several challenges with parsing this file. The records span multiple lines, where the first line is a datetime and the second line is a JSON encoded structure. Additionally, the last field in this JSON structure embeds yet another JSON encoded structure as a string. Therefore, we would like to parse this file into the following table, where the first column is a datetime, followed by the fields from the JSON structure, including the last embedded field. Let us see how to parse this file. I tried this exercise using Python in the notebook environment, using a standard data manipulation and analysis library, pandas. It started with some struggle and looking through the Python regular expression documentation. Then some more cycles of struggle and searching for online help. And in around 30 minutes, I managed to produce working code. Let us now see the steps required to parse this file on a cleaned up version of my Python code. This task is naturally composed of 4 distinct steps. The first step is to split the file into records, using a regular expression that looks for lines that start with a number. The second step is to split the records into 2 lines and optionally parse the first line into a datetime object. The third step is to extract the JSON structure from the second line. And finally, the fourth step is to extract the JSON structure embedded in the last column. This is not an easy task to accomplish in Python. That is why the program synthesis community has developed numerous techniques, either by example or automated, that can help with the individual steps discussed here. There are already many existing approaches and tools that can handle different formats, like web pages, CSV, custom log files, JSON, and many more. While these tools achieve impressive results on their respective domains, they're also restricted by underlying DSLs or templates. Hence, none of those techniques can communicate with other approaches and handle a mixture of formats, like for example, JSON embedded in CSV or log file. Although some of the approaches might handle files like the one we have just discussed, they are often very dependent on a syntactic structure of a file and cannot handle small variations like reordering or missing JSON keys. In Unravel approach, instead of developing a complicated DSL or templates, we embrace the diversity found in text files. Unravel is an extensible framework with parametrized cooperative rules that communicate with and transform data that we call partial structures. Intuitively, a partial structure is an arbitrary tabular interpretation of the input file. Consider the following input text file that uses comma and semicolon to delimit various table columns. The whole input file as a one-by-one table is a partial structure. The result of splitting the lines by the comma delimiter is another partial structure. And the result of splitting the lines by the semicolon delimiter is yet another partial structure. Partial structures can be combined to form a new partial structure. For example, the comma split partial structure and the semicolon split partial structure can be combined to a partial structure split by both delimiters. We can also apply a rule to a partial structure in order to obtain a new transformed partial structure. For example, JSON rule parses a JSON encoded string and flattens the obtained tree into the table using the parameter expression s. In this example, the flattening expression selects the fields message, OK, and the first and the second elements of IDs. Learning such an expression s is an active area of research. Finally, we point out that this rule easily handles missing and reordered JSON keys as seen on the last row. In general, any black box rule from the program synthesis literature, predictive or by example, can be plugged to extend the framework. Like for example, flash extract, column split, or extraction web. On a high level, the framework learns a sequence of parametrized rules and applies those rules starting from the input file and finally producing the resulting table. Let us now see how the Unravel algorithm learns rule sequences and their parameters. The algorithm maintains a collection of partial structures. And initially, the collection only contains the partial structure that considers the whole file as a one-by-one table. The algorithm picks an existing partial structure and some rule, and using either predictive synthesis or user-provided examples, learns a parameter instantiation for the rule. By applying the learned rule to the partial structure, a new partial structure is obtained, and the algorithm adds this new partial structure to the collection. This process is repeated until no new rules can be learned. At this point, the algorithm merges partial structures into tables, ranks the resulting tables, and returns the top-end results to the user. Let us now see the Unravel algorithm on the example input file that we saw earlier. The algorithm starts with the input file as the only partial structure. In the first step, the algorithm applies the Radiček split rule with a regular expression parameter that splits the input file into records on the lines that start with a number. To learn this regular expression, the algorithm uses a predictive synthesis algorithm from the literature. At this point, the algorithm also learns other parameter instantiations for Radiček split rule, as well as other rules from the same starting partial structure, and adds the resulting partial structure to the collection. For example, the algorithm also learns the delimiter split rule with new line parameter, which results in a partial structure where each line is one record. In the second step, the algorithm learns, on the partial structure obtained in the previous step, the string split rule with a delimiter parameter that splits the records into two lines. The algorithm learns the delimiter string by extracting all possible delimiters from the input and using the ones that give consistent results across all records. Same as in the previous step, the algorithm also learns other delimiter instantiations as well as other rules from the same starting partial structure. In the third step, the algorithm applies the JSON rule to the second column of the partial structure from the previous step and extracts a new partial structure. Similarly, in the fourth step, the algorithm again applies the JSON rule to the last column of the partial structure from the previous step and obtains the table from it. Finally, when there are no rules to be learned, the algorithm extracts tables from partial structures and ranks them. The ranking aims to maximize information content of the extraction. The desired table in this example is ranked over other obtained tables because it extracts the most information from the input file. The resulting ranked tables and the resulting sequences of rules are finally returned to the user. What happens if the predictively learned table is not what the user wanted? Or if the user wants to further split some columns or merge some oversplit columns? In a traditional setting, the user would have to go back and give lots of examples. That is, most of the existing synthesis approaches are either completely by example or completely automated. The problem with the by example only systems is that the user has to do too much work and the process is error prone. On the other hand, problem with purely predictive systems is that artificial intelligence cannot always work. That is, it will fail for some edge cases, or it will not be able to guess the user's intention, as intention might vary from one use case to another. Rather than taking one or the other side, in the Unravel approach, we embrace the mixed interactivity model. That is, we aspire to make the approach as much predictive as possible, but on the other hand, allow the user to help the algorithm at any point. This is enabled in two ways. First, at any point during the algorithmic search, the user might choose which rule should be applied next. Second, the user can also provide examples on any intermediate step in the algorithm. Consider the following table where the algorithm determined these records predictively, but then it got stuck. The user observes the table and determines that there are two types of records, and hence the user indicates that she wants to use the pattern partition rule that partitions records in several groups. The user also provides examples of records, one for each of the two groups. The algorithm then learns the regular expression to distinguish two record types, and after that it is able to continue in predictive mode and learn the following two tables. We have implemented the proposed approach in a prototype and evaluated it on over 600 real-world text files. Unravel is able to predictively extract the intended table in 90% of the cases. And by using user-provided examples, it is able to handle 62% of the remaining cases. The implementation could be further improved by plugging new rules and by making the rule inference more intelligent for the existing rules. Finally, in our evaluation, we found that 50% of real-world text files require application of more than one rule to extract the desired table, indicating that real-world files are often irregular and of mixed formats. Technologies like Unravel are already shipped in real-world commercial applications, as for example Microsoft Power BI. We next show two demos for similar synthesis technologies developed by the PROSE team and shipped in Power BI. In the first demo, the user uses Power BI to extract a table from the log text file by using examples. The user only needs to select a file, enter example for each output column, and the extracted table is there. We also see that Power BI uses very similar steps to parse the file as the Unravel learns automatically. In the second demo, the user extracts a table from a web page, in this case from the Internet Movie Database of best action movies. To extract this data using Power BI, the user only needs to enter an URL and wait for the predictive synthesis technology to do the heavy work. We are also working on using Unravel to improve upon these existing tools. To summarize, we have discussed a novel framework for parsing text files in various mixed formats. The framework allows combinations of various previous research on this topic in a cooperative and extensive way. Finally, we have explored the rich setting of interactivity where we strive to be as automated as possible, but allow the user to intervene when there is ambiguity or the AI tool is stuck. Thank you for your attention.